So in the previous installment, we met the cast of characters, all the forces, and we learned about this angle theta. And I promised you we would prove that this theta, this angle, equals this angle in here. So the first thing for us to realize is that we have two forces that we can always draw, and the first of them is the force of gravity, or the weight, oriented like so. Now, what is not so obvious is that if we look at the base of this triangle and the incline, well, this is the horizon. It's the surface of the Earth. And the Earth is very, very large, which makes this a tangent to the surface of the Earth. The object resting on the inclined plane, depicted by the red dot, it is being attracted to the center of the Earth, and the center of the Earth is being attracted by it. So there is this force of attraction between the two of them, between the centers. So that means that this force, like so, that's directed, is directed to the center of the Earth. And if way somewhere down here we have the center of the Earth and this line passes through it, well, of course, then this represents a radius. And we know that a radius to the circle, all tangents are perpendicular. Aha, so we have a radius going through the center of the Earth that intersects a tangent, so it's perpendicular to that tangent. And so now the angles here around this particular point in the center, I am going to label as A, B, C, and D. We have the blue vector representing the weight, which is a straight line. And a straight line we know adds up to 180 degrees. And if D is 90, then that means A is 90, and it's perpendicular as well. And you can use that same reasoning to demonstrate that B is also perpendicular, and so is C. Of course, once we showed that D was, we could have used vertical angles to get to B, and then straight line. There's a lot of ways we could go about doing that. But the short of it is we now know those are all right angles. So that means in our first triangle, which I am going to outline in blue, let me do that nicely. So in our blue highlighted triangle, which we will call A theta, and I will call it A theta and M. We know that's a triangle. We know the sum of the angles of a triangle are 180. So we know that A plus M plus theta equals 180. But we know A is 90. So 90 plus M plus theta equals 180. So we know then that M plus theta is 90. And so M plus theta equals 90. So that's what we know about that triangle. Now we are looking for this other angle here. So let's do a similar thing we did below and name the angles here. And I'm going to start with angle E. We will call this E, which is a 90-degree angle. And we know that because it is the force normal. By definition, it is drawn and constructed perpendicular to the surface, so that makes it easy. And of course, we can use our straight line being 180 degrees to show that this is also perpendicular. And we can use it again to show that that is perpendicular. And then we can also show that this angle here, H, is also perpendicular. So that leaves one small angle, the angle in question. And let's call that angle in question K. Well, what do we know? We know that M plus K equals H. And we know M plus K is H, and H is 90. So we have M plus K is 90, and we have M plus theta equals 90. In that case, since we have two expressions that have m in them, we can solve the bottom one for m, and we know that then m is 90 minus theta. Now taking this expression and subbing that in, we get m, which is 90 minus theta plus k equals 90. Subtracting 90 from both sides gives us negative theta plus k equals 0. So if negative theta plus k equals 0, then k equals theta. So we have just demonstrated that this angle k is equal to theta, using nothing more than straight lines and some of the being 180 and some of the angles of a triangle being 180, and the definition of a right angle being 90. So we have just demonstrated that this theta is indeed this angle k, and therefore they are equal to each other.